So we begin this course by defining covering maps. And proving some lifting theorems for them. So a definition of an evenly covered neighborhood so let f from x to y be a continuous map a neighborhood v in y is said to be evenly covered if f inverse v breaks up into a disjoint union of ui's where each ui is open in X and f from ui to v is a homeomorphism. So this is easiest explained by seeing some examples. So the first example we'll take is let f from R to S1 be the map so let A strictly less than B be real numbers. Define an open set VAB contained inside S1 as the image of those theta such that theta lies between A and B. So in terms of a picture, so if this is A and this is B, then VAB is this open set. So we claim that if B minus A is strictly less than 1, then VAB is evenly covered. By F. So in fact, F inverse VAB breaks up into disjoint union of n in integers a plus n comma p plus n. So the picture looks like this. This is my 0, which goes to 1. So here is my VAB. The inverse image of that is going to be here. And clearly, f from a plus n, b plus n to VAB is a homeomorphism. On the other hand, if b minus a is strictly greater than 1, then VAB is equal to S1. And so F inverse of VAB is equal to R. So in this case, VAB is not evenly covered. Because if it were evenly covered, as if it were evenly covered, then we would be able to write the real line as a disjoint union of open sets, each UI open in R, and F from UI to S1 a homeomorphism. This is not possible since an open subset of R cannot be homeomorphic to S1. Let's see another example where we restrict the above function to the positive reals. So then we have 0 here, 0 is 1, 2, and so on, and there is mapping to S1. So if we take any point x in S1 such that x is not equal to 1, then so this is my x, then we can take a small neighborhood V of x which does not contain 1, so my V is over here, and one easily checks that P is evenly covered. However, there is no evenly covered neighborhood of 1, which we now show. So for this, Notice that if U contained in V is open and V is evenly covered, then U is evenly covered. Thus, if there is a neighborhood of 1 which is evenly covered, then we may find a small epsilon positive such that V minus epsilon epsilon is contained inside V, and hence V minus epsilon epsilon is evenly covered. So this implies that, this implies now F inverse V minus epsilon epsilon breaks up into a disjoint union. This is easily checked. N greater than or equal to 1 minus epsilon plus 1 comma epsilon plus 1. So by assumption, V minus epsilon epsilon is evenly covered, and so F inverse V minus epsilon epsilon breaks up into a disjoint union of ui's, and each ui is homeomorphic under F to V minus epsilon epsilon. In particular, this implies that each ui is connected, which implies that ui's are precisely the path components of F inverse V minus epsilon epsilon. So let U0 be the path component of, let's say, epsilon by 2, then clearly U0 is forced to be the set 0 epsilon. However, the map F from 0 epsilon to V minus epsilon epsilon is not even surjective. This gives a contradiction. Thus, there is no neighborhood of 1 which is evenly covered. So this brings us to the definition of a covering map. A map F from X to Y is called a covering if each Y in Y has a neighborhood, let's denote it P sub Y, which contains y, which is evenly covered. By f. Thus, from what we just saw, f from R to S1 is a covering map. Similarly, the map C to C star, Z goes to e to the power Z, is a covering map. The restriction is not a covering map. So the Z goes to Z power n is a covering map. If fi's from xi to yi are coverings, then f1 cross f2 from x1 cross x2 to y1 cross y2 is a covering. If f from x to y is a covering and z contained in y is a subspace, then f from f inverse z to z is a covering. So let's now prove a simple proposition about covering maps. So these examples are left to the reader to work to show that these are covering maps. P a covering map, then F is open. So the proof goes as follows. So let x in U be a point. So let V be a neighborhood of f of x in Y, which is evenly covered. So we may write f inverse V breaks up as disjoint union of Wi and say x is in U intersection Wi naught for some I naught, which is an open subset of Wi naught, since U is open inside X. Since f from Wi naught to V is a homeomorphism, This implies f of u intersection wi naught is an open subset of V which contains f of x naught. Thus, f of x naught is contained in f of u intersection wi naught, which is contained in f of u, and this is open in V, and since V is open in Y, so this implies this is open in Y. So this implies that f of u is an open set, which implies f is open. Now let's prove the two most important theorems of this first lecture. This is the path lifting theorem. That f from x to y be a cover. Let g from 0, 1 to y be a path. Let g of y naught be denoted, g of 0 be denoted by y naught, and let x naught in x be a point in the fiber of y naught, that is f of x naught is y naught. Then there is a unique lift g tilde from 0, 1 to x such that g tilde of 0 is equal to x naught. So what this is saying is we have x to y, here we have g, and there is a unique map g tilde such that g tilde of 0 is equal to x naught. So the proof proceeds as follows. So we cover y by open sets Vi, which are evenly covered. Then we can pull back this cover and write 0, 1 as a union of G inverse Vi by the Lebesgue number lemma. We can choose a n very large such that we can break our 0, 1 into intervals of length 1 upon n, and we have each of these intervals is contained in Vi for some I. So we will first lift G on the interval 0, 1 by n. So how do we do this? So we have 0, 1 by n, and the image of this maps into some evenly covered neighborhood, which we call, let's call it V0, and F inverse V0 breaks into a disjoint union of, let's say, U0i, I is in I. So we have V0 like this. This is our path. This is Y0, which is G of X0. Sorry, G of 0. And the inverse image of V0, it breaks up into various sheets, and one of these sheets will contain X0. So assume X0 belongs to U0, J. Since F from U0J to V0 is a homeomorphism, denote its inverse by S. Define. So we have the inverse to be S over here. So this is my F. And here 0, 1 upon n to V0 we have G. So define G tilde. So let's call it G tilde 0 by S compose G. Now let us denote G. Okay, so before that, clearly G not tilde, G tilde 0 satisfies F compose G tilde 0 is equal to G, and G tilde 0 of 0 is X0. So now let G of 1 upon n be Y1, and let G tilde 0 of 1 upon n be X1. Then F of X1 is equal to Y1. So we now lift G on 1 upon n to 2 upon 2 by n to X using the same method. in such a way to define g tilde 1 from 1 upon n, 2 upon n to x such that g tilde 1 f compose g tilde 1 is equal to g, and g tilde 1 of 1 by n is equal to x1. So we have this interval 1 by n, 0, 2 by n. Here we have defined g tilde 0, and here we have defined g tilde 1, and g tilde 0 of 1 by n is x1, which is equal to g tilde 1 of 1 by n. Thus, we can put these together to get a continuous map which we have used notation and denote g tilde 1 from 0, 2 by n to x such that g tilde 1 of 0 is x naught, and f compose g tilde 1 is g1, is g, sorry. And now we do the same thing. We proceed inductively now. So define g of 2 by n to be y2 and g tilde 1 of 2 by n to be x2, and proceed in this fashion. So this implies we get a lift g tilde from 0, 1 to x So let us now prove uniqueness. Of the lift. Suppose there are two lifts. G tilde and H tilde, such that G tilde 0 is x naught and H tilde that's equal to H tilde 0. So both of them are lifts of G and they start at x naught. So we consider the set T is those x in 0, 1 such that G tilde of, let's say, y is equal to H tilde of y for all y lying between 0 and x. Clearly 0 belongs to T, thus T is non-empty. Let T naught be the supremum of T and assume T naught is strictly less than 1. So then we will arrive at a contradiction Since x is Hausdorff, by taking a sequence Tn converging to T, we see that G tilde of Tn conjugate T naught. T naught is equal to H tilde of T naught. So we want to analyze what happens in the set T naught comma T naught plus epsilon. So choose epsilon positive, very small, such that G of T naught comma T naught plus epsilon is contained in V, which is evenly covered. So we have T naught. This is V. So V breaks up into, the inverse image breaks up into various sheets, and we have this map G tilde, and we also have H tilde. So both G tilde and H tilde, they agree on T naught, but they seem to branch off at T naught. So from this we will get a contradiction. This common point is T tilde of T naught. So F inverse V, let us write it as disjoint of ui's, and suppose G tilde of T naught belongs to U0. Then, since T naught comma T naught plus epsilon is connected, it follows that G tilde of T naught comma T naught plus epsilon is also contained in U naught, and H tilde of T naught comma T naught plus epsilon is contained in U naught. So let us restrict our attention to these maps G tilde and H tilde from T naught comma T naught plus epsilon to U naught. Now on U naught, so we want to prove that both these maps are equal on the interval T naught comma T naught plus epsilon. But to say that both these maps are equal, since F is a homeomorphism, it's enough to show that F compose, so both F compose G tilde and F compose H tilde are equal to G. Since F is a homeomorphism, on U naught, this implies G tilde and H tilde agree on T naught plus epsilon. But this contradicts that T naught is equal to suprema of T. This completes the proof of uniqueness. The proof of uniqueness, and so the proof of the path lifting theorem. So we will end the lecture by proving one more lifting theorem. The idea is very similar. Lifting theorem for homotopies. Again, let f from x to y be a covering. Let f from I cross I to y be a map. Let f of 0, 0, let's call it y naught, and choose x naught in x such that f of x naught is equal to y naught. Then there is a unique f tilde from I cross I to x such that f compose f tilde is f and f tilde of 0, 0 of the origin is equal to x naught. So proof. So proceeding as in the previous proof, we may cover y by vi's and find an n sufficiently large such that we can break I cross I into squares of side length 1 upon n, and for each of these squares, so let's call this, say b1, b2, we number the squares like this. F of bi is contained in bj for some evenly covered neighborhood vj. So as before, we will proceed inductively. So we first lift the map on B1. Suppose f of B1 is contained in V0, so V0 is evenly covered. Then we write f inverse V0 as a disjoint union of u0i 9i, there is a unique j such that x0 is in u0j. Let S from v0 to u0j be the inverse of f. So define f tilde on b1 by f tilde is equal to S compose f. Clearly, f compose f tilde is equal to f, and f tilde of 0, 0 is equal to x0. So let us assume that we have lifted f on z, which is the union of the first L PS. Suppose that f of PL plus 1 is contained in V, an evenly covered neighborhood. Let T be the intersection of Z with PL plus 1. So either T can be some line segment like this, or it can be some line segment like this. So in either case, clearly T will always be connected. Thus, if F inverse V is a disjoint union of open sets I, ui, then the image f tilde of T which is defined, since f tilde is defined on Z and T is a subset of Z, is contained in uj for some j. Since T is connected. Let S from Vj to Uj, from V to Uj, denote the inverse of F. Denote the inverse of F restricted to Uj. Consider the map. H from BL plus 1 to Uj defined as H is equal to S compose F. So we claim that H and F tilde agree on T. So once again, as we had using the same method that we saw before, H and F tilde, these are maps from T to Uj. And to check that they are equal, we can check after composing the homeomorphism that they are equal. But this is clear since F compose H is equal to F compose F tilde is equal to F on T, and F is a homeomorphism. On Uj. Thus, H and F tilde can be put together, can be glued to give a continuous map Z union BL plus 1 to X, which again we denote by F tilde, and obviously F compose F tilde is equal to F, and F tilde of 0, 0 is equal to X naught. So proceeding in this fashion, we see that F tilde is defined on all of I cross I. To prove uniqueness, suppose F tilde and G tilde are two lifts. Such that F tilde of 0, 0 is X naught is G tilde of the origin. Then applying path lifting, unique path lifting, to so this vertical line, which is 0 cross I, we get that F tilde is equal to G tilde on 0 cross I. Now we fix any T, so in particular F tilde 0 comma T is equal to G tilde 0 comma T for all T. So fixing a particular T, and applying unique path lifting, to I cross T, we get that F tilde is equal to G tilde on I cross t for all t, that is f tilde is equal to g tilde. So this completes the proof of the theorem. And before we end, let us see one more lemma, a useful lemma which we will use later. So let the notation be as before, and suppose f of 0 cross I is y naught. Then f tilde, which is the unique lift starting at x naught, similarly, suppose f of 1 cross I is y1, then f tilde of 1 cross I is also constant. So what this lemma says is that if f is constant on this line, then f tilde is also constant on this line. So what is the proof? The proof is very easy. Clearly, f tilde of 0 cross I will be contained in f inverse of y naught. But f inverse of y naught is a discrete set. This is clear because we can take clear by taking an evenly covered neighborhood of y naught. So since 0 cross I is connected, it follows that f tilde of 0 cross I is constant and so is equal to x naught. So similarly for 1 cross I. So we will end here.